Hello everyone, and welcome back again to another video on calculus. In this video we will be covering how to integrate some more basic functions. Specifically, we'll be taking a look at the exponential and logarithmic functions. So the first rule that you should know is that whenever you want to integrate a function of the form a to the power of x, where a is a constant, then the integral of that function will just be a to the power of x divided by the ln of a plus c, of course. And of course, this works for a being a constant. If you had the integral of x to the power of x dx, you cannot just use this rule and say that's going to be x to the power of x divided by the ln of, not 7, the ln of x plus c. Okay, it doesn't work like that. A has to be independent of x. Okay, and the proof for why this rule works is fairly simple. We can start by writing out the derivative rule for exponentials, because for exponentials, differentiating and integrating is pretty similar. They only vary by this constant factor of the ln of the base. So let me show you how it's derived. We know that the derivative with respect to x of a to the power of x is a to the power of x times the ln of a. Next, we can integrate both sides. So we get that the integral of the derivative with respect to x of a to the power of x dx. Sorry, let's just leave it like that. Is equal to the integral of a to the power of x times the ln of a. Next, the integral and derivative will cancel out, so we're just left with a to the power of x equals, and now remember we defined a to be a constant, so the ln of a will also be a constant. So we can pull it outside of the integral and get this, and we need a dx since we're integrating with respect to x. And then we can just divide both sides by the natural logarithm of a to get that the integral of a to the power of x dx is equal to a to the power of x over ln of a, and we just add a plus c since we have an indefinite integral. So there we go. That's to show why this rule is correct. You don't have to do this every time you use it to solve an exercise. This is just, it could help you remember it if you know how it's derived. Now let's move on to the next one. I've actually forgotten to write it, but the integral of ln x dx is x times the ln of x minus x. And I don't think there is a way for you to find this out by yourself with the current techniques that we've mentioned on this channel so far. But yeah, so in fact you need integration by parts to get to this result, plus c, sorry. But I can confirm that this is true by taking the derivative of this and showing you that it leads to ln of x. So when you derive this with respect to x, you get, you need to use the product rule. So you get x times 1 over x plus 1 times ln x. When you derive minus x, you get minus 1, and when you derive the constant, you get 0. So when you sum all of these up, this is just 1, this is just ln x. So together, 1 and minus 1 cancel out, 0 is just 0, so you're just left with ln x, which is what we have over here. So this shows that this rule is actually correct. And now you might be wondering, well, ln x is just the logarithm in base e of x. What if we have the integral of the logarithm in another base a of x, where a can be 3 or 4 or 5 and so on? How can we integrate that then? Well, we'll see a few of those examples, but the key is to use the change of base rule to rewrite it as a natural logarithm. So let's get started with the integral of 5 to the power of x dx. We can just simply apply this rule. So it's just copying a formula and inputting our values. So it's going to be 5 to the power of x over the ln of 5 plus c. Next, the integral of e to the power of x dx is just e to the power of x plus c. Remember, e to the power of x is a function which is its own derivative. So the integral of e to the x and the derivative of e to the x are both just going to be e to the x. But of course, if you have an integral, you also have to add plus c. An indefinite integral, that is. Okay, so next we have the integral of 2024 to the power of x plus 2024. And what we can do is use exponent laws to break this down into 2024 to the power of x times 2024 to the power of 2024. So this is what we're integrating with respect to x. Remember, now this is a constant. It may be very big, but it's a constant, so we can actually pull it outside of the integral. And then we just have to integrate 2024, which is, again, another straightforward application of the exponent, the integral of an exponential function rule. So we are going to have this 2024 to the power of 2024 constant as a constant multiplier. And then to integrate this, we just get 2024 to the power of x over the ln of 2024 plus c. And yeah, now you have the same base over here, so, and the two are multiplied, so you could combine this into a single as 2024 to the power of 2024 plus x, but I'd say you don't have to do that. I'd say this form is simple enough. It's up to you. So let's just move on to the next one. Now, generally when you're dealing with integrals, you prefer sums and differences over products, because of the rule that the integral of f of x plus g of x dx can be broken down into the integral of f of x plus the integral of g of x, of course with dx's, but the integral of f of x times g of x is not necessarily equal to, with dx again, f of x, the integral of f of x dx times the integral of g of x dx, okay? So we can't just break down this multiplication into the integral of this times the integral of that, okay? That's not allowed. And that is why it's just, in general, easier to work with integrals of sums of functions instead of products or divisions. For products, we have rules like use substitution and integration by parts, but since we haven't seen those yet, we want to rewrite this as an addition, and a great way to do that is by expanding. But first, to simplify our lives and the expansion, we can factor out a minus, okay? So, and I'll factor it out of this bracket, because you'll notice when I do that, I get a difference of 2 squares. Remember, a minus b is equal to negative b minus a. And that's the rule that I'll be using to factor out a minus from the second bracket. So we can rewrite this as negative, and I'll pull it out of the integral as well. Negative integral of e to the power of 4x plus 1 times e to the power of 4x minus 1. And just like that, we get a difference of 2 squares factorized form by factoring out this minus. So now I'm going to use another rule, which says that a squared minus b squared is equal to a plus b times a minus b. Okay. So in this case, my a is going to be e to the power of 4x, and my b is going to be 1. So I can expand it and write it as the integral of e to the power of 8x. Since we have to square it, we're going from here to here. And then we're going to have minus 1 dx, right? And we can now distribute this minus back inside, as well as split the integral. So we can write this as the integral of 1 dx minus the integral of e to the power of 8x dx. Okay, this step should be clear. Now the integral of 1 dx is x, and the integral of e to the power of 8x is going to be, well, we can consider this as e to the power of 8 and then to the power of x, where e to the power of 8 is just a constant. So we can say that the integral will be e to the power of 8 to the power of x divided by the ln of e, okay, and divided by 8, because of the 8 over here, okay? And we can write this in a simpler form. Let's write this as e to the power of 8x over 8. There we go. And yeah, when you differentiate this, the 8 comes down and cancels out with the 8 on the denominator, and we're just left over with e to the power of 8x. So, oh, sorry, I deleted it. There we go. Let's write the final answer up here. X minus e to the power of 8x over 8. There we go. Plus c. Next question, we have the ln of 5x cubed. And I can just use 2 log rules to simplify it. One of them being that log of AB is log A plus log B, and the other that log of A to the power of B is the same as B times the log of A. So I'll use both of these to rewrite this as ln of 5 plus 3 ln x. And then when you integrate, ln of 5 is just a constant, and the integral of a constant is that constant, ln 5, times x, okay? And then we have plus the integral of ln x we saw was, oh, I must have deleted it again, x ln x minus x. So we get plus 3x ln x minus x. And if you were to fully expand this out, you can say x ln 5 plus 3x ln x minus 3x. Okay. That is the final answer. And I mean, you can factorize this, but let's just leave it in expanded form. So x ln of 5 plus 3x ln x minus 3x plus c. Okay. Next question. Log base 7 of x. So we finally have this example of where we have to integrate a logarithmic function, but the base is not e. We have base 7. So as I hinted at the beginning of this video, what you can do is rewrite log base 7 of x as ln x over ln 7. Okay, and this is a property of logarithms. It's called the change of base rule. And what's really helpful here is that we know the integral of the ln of x, and the ln of 7 is nicely just a constant. So we can actually pull that outside of the integral. So we can say that this is the same as 1 over ln 7 times the integral of ln x dx. Okay? And be careful when you do this thing where you pull things outside of the integral. Whenever you do that, make sure they really are a constant. And a constant is just anything that's independent of x. Okay? So containing only numbers or functions of numbers, but no x's. It has to be independent of the variable. And now the integral of ln x, we had it before. We can just say as a final answer that this is x ln x minus x over the ln of 7 plus c. So I'll make some room. Might need to delete an equal sign. There we go. Okay, next question. We have another function of the form a to the power of x. You might say it's a to the power of e times x, but not really. We can rewrite it in the form a to the power of x using exponent laws. E to the power of e times x is just the same as e to the power of e to the power of x. Okay, and this is just a constant which we can call our a. So according to the rule, this is the integral of e to the power of e to the power of x dx. When you integrate that, you get e to the power of e to the power of x divided by the ln of the base, which is e to the power of e. And now we can pull this e outside of the ln. And remember, ln of e is just 1. So I can expand this out. I get e to the power of ex divided by e times the ln of e. And ln of e is just 1. So we get e to the power of e times x over e, or e to the power of e times x minus 1. Like that. Okay. Next, we have the integral of the logarithm in base x of x. Let's see. Can we just do the same thing that we did here? Can we do that? Can we say that this is just equal to x ln x minus x divided by the ln of x? Since that's the same, we just replace the 7 with an x, since that's our base. No, and I'll show you why. We can't do that. What we did before was rewrite we rewrote it as the ln of this divided by the ln of the base. So log base x is equal to that. Log base x of x is ln x over ln x. And you might say, well, isn't that just 1? Yes, it is, because this is the exact same as the denominator. And that makes sense. Log base a of b is asking, what power do you have to raise a to get b? And if you apply that on log base x of x, you ask, what power do I have to raise x to get x? And that power is going to be 1. So the integral of 1 dx is always going to be x plus c. So that's the answer to our integral. So don't always just copy what you had before and adapt it, but actually try to critically think about what the function actually is, and in this case it's just a constant. So we get x plus c. Okay. Next, next one. Or actually, before we move on, I want to point out a common mistake. So if you were to rewrite this as the integral of ln x over ln x, of course this is just 1. But if you were to not notice that, for example, then, for example, if there was a square here, ln of x squared, or that's, so ln of x squared. What we did before was pull this outside of the integral. Let's remove the square, actually. That might be too complicated. We pulled it outside of the integral, and then we had to integrate ln of x, right? But we were only allowed to do that because we had ln of 7, which is a constant. Here we have ln of x, meaning that it's not a constant. Its value is dependent on x, so we cannot do that, okay? So the correct answer is, of course, x plus c. Next, we have the integral of log base 3 of x to the power of 5 plus log base 11 of x to the power of 13. So let's use our log rules to rewrite the integrand as 5, or rather 5 ln x over ln 11. Ln of 3, since that's our base, plus 13 ln x over ln 11. And from here, integrating this is easy. You just get 5 times x ln x minus x over ln 3 plus 13x ln x minus x over ln of 11 plus c. Okay, that's the final answer. Next one, we have the integral of 2 over x ln 3. Now, what you can do is pull these constants, 2 and ln of 3, outside of the integral, and then you just have the integral of 1 over x, which is, of course, the natural logarithm of x. Right? The integral of 1 over x dx is ln x. Don't use the reverse power rule and write this as x to the power of minus 1. Don't do that. This is the natural logarithm of x plus c. So you can do that. You can bring these 2 and ln of 3 outside since they are constants. But what you can also do is only pull the 2 outside and recognize that 1 over x ln 3, its integral, is just log base 3 of x. And since you've also pulled the 2 outside, you know that this is 2 times the log in base 3 of x plus c. Okay, next question. 5 to the power of x to the power of 7 times 7 to the power of x to the power of 5. Now what you can do is exchange these 2 exponents as well as these 2 over here. So we can rewrite this as the integral of 5 to the power of 7 to the power of x times 7 to the power of 5 to the power of x. I'll actually move this down to here so I have more space. And now don't try splitting the integral. Don't write equals the integral of 5 to the power of 7 to the power of x times the integral of 7 to the power of 5 to the power of x. Okay, don't do that. Because, again, you can't split a multiplication like that. And then don't try to just use the normal exponent rule from here. This step is actually wrong, as I've highlighted here. But what you can do instead is combine these 2 using exponent laws. Remember, this is just the same as 5 to the power of 7 times 7 to the power of 5, all to the power of x. And this is just going to be our a. And it is a constant, so we're good to use the rule. So we get this to be 5 to the power of 7 times 7 to the power of 5, all to the power of x, divided by the ln of the base, 5 to the power of 7 times 7 to the power of 5. And that's it, plus c, final answer. Now, in the next exercise, we're going to do something similar, but with another method. So the first step, A, is to rewrite 5 to the power of x times 7 to the power of x in the form g to the power of f of x. And I should specify here that g is a constant. Okay? And this A part specifically doesn't have much to do with calculus. It's just manipulating using exponent laws. But it's used for part B to determine the integral, to determine an integral. So we want to, our last step is going to be that A to the power of x times B to the power of x is equal to AB to the power of x. Or we can even replace this by f of x's. So A to the power of f of x times B to the power of f of x is the same as AB to the power of f of x. And why should we do that? Well, remember, we need to get to this form, g to the power of f of x. We have our f of x, and our g can be a times b, because we have this 5 to the power of x and 7 to the power of x. So that can be our two components over here. And but what we have to do before that is to get our common functions over here. So, or that's one option, or we can get a common base. So a to the power of f of x times b to the power of, times a to the power of g of x. We know that this is the same as a to the power of f of x plus g of x, okay? So that's an alternative. We can also use this rule, and this form is the same as that form. We can just say that our f of x is the sum of these two functions. So we have to use one of these two rules. And let's try using this rule. So getting a common base over here. Since now we have a base of 5 and a base of 7, let's try to get a common base with with varying functions on top. And one way that we can do that is by rewriting 5 as 7 to a function f of x. And that allows us to change our base. Now, what is this function f of x? Well, we don't know yet, but we can solve for it by taking a log in base 7 of both functions, of both sides. So on the left side, we get log base 7 of 5, and on the right side we get log base 7 of 7 to the power of f of x. Log base 7 and 7 cancel out, so we get f of x to be log base 7 of 5. So 5 equals to 7 to the power of log base 7 of 5. Okay, so let's substitute 5 in here by 7 to the power of log base 7 of 5. So we get 5 to the power of x times 7 to the power of x equals 7 to the power of log base 7 of 5, all to the power of x, times 7 to the power of x. And what we can do now is just use exponent laws. This is just 7 to the power of x times log base 7 of 5 plus x. Okay? And that's it. We've managed to rewrite 5 to the power of x times 7 to the power of x as 7, a constant to some function. in this case our function is x times log base 7 of 5 plus x. Okay? So now let's do b. We have to evaluate the integral of 5 to the power of x times 7 to the power of x dx. Now, of course, we can just say that this is the integral of 35 to the power of x dx. And then you can apply the rule for integrating exponentials. Say that this is 35 to the power of x over the ln of 35 plus c, so on. But it says hence, so we should use what we previously found. So let's do that. We can substitute 5 to the power of x times 7 to the power of x by the integral of 7 to the power of x log base 7 of 5 plus x dx. Okay? Sorry, this plus x should be a part of the exponent. There we go. So, how do we actually integrate this exponential? Well, we can either factor out an x and then use the exponent laws, or we can solve it. Remember, the integral of a to the power of f of x. How do we know what it is? Well, we can think about the derivative of a to the power of f of x. And what is that? Well, it's a to the power of f of x times f dashed of x times the ln of a. And then we can integrate both sides with respect to x. The integral and the derivative cancel out, so we get a to the power of f of x equals to the integral of a to the power of f of x times f dashed of x times the ln of a dx. Now, considering that f dashed of x is a constant, we can pull it outside of the integral. So remember, this rule is only going to work when the derivative is a constant, which means that this exponent has to be a linear function, which it is in our case, okay? And if it is, the ln of a is also constant, so what we can do is pull those outside of the integral. We get a to the power of f of x equals to 1 over, not 1 over, sorry, f dashed of x times ln a times the integral of a to the power of f of x dx. And then we can divide both sides by this. So we get the integral of a to the power of f of x equals to a to the power of f of x over f dashed of x times the ln of a, and we should add a plus c. So we can apply this on our integral over here. Our a to the power of f of x is going to be 7 to the power of x log base 7 of 5 plus x. And then we have an ln of 7. And f dashed of x is the derivative of the exponent, which is log base 7 of 5 plus 1. Yes. And then you can simplify further, but I'd say we end here. So thank you everyone for watching this video, and I look forward to making the next one, which will most likely be all about integrating trigonometric functions, most likely. And then after that, we'll move on to actual integration techniques, such as U substitution, integration by parts, integration by factorizing into partial fractions, and so on. So see you guys in the next video.